Hello, my name is Jehnya. I am a part of Group 13, and this semester we worked on our project Antoine equation. Chemists often use Clapeyron-Clausius equation to estimate the vapor pressures of pure liquids or solids. Several of the assumptions made in the derivation of the equation fail at high pressure and near the critical point, and under those conditions, the Clausius-Clapeyron equation will give inaccurate results. Chemists still like to use the equation because it's good enough in most applications and because it's easy to derive and justify theoretically. Chemical engineers sometimes need more reliable vapor pressure estimates, and the Antoine equation is a simple 3-parameter fit to experimental vapor pressures measured over a restricted temperature range. You can see the equation here, where A, B, and C are Antoine coefficients. These vary from substance to substance. They also have separate sets of Antoine coefficients, as do components in mixtures. The Antoine equation is accurate to a few percent for most volatile substances. The goal of our project was to use Antoine equation to determine the vapor pressure given temperature, or the temperature given vapor pressure, depending on the user's choice. Then take the vapor pressure and temperature given by Antoine equation and use it with Clausius-Clapeyron equation to find the heat of vaporization. The initial vapor pressure for the equation will be found by determining the vapor pressure of the substance at room temperature, and the outputs we were expecting from writing this code are right here, and they were to be different depending on the user's choice of compound. These outputs would be the boiling temperature, heat of vaporization, equations for the line of heat of vaporization, vapor pressure, and polynomial regression line. Again, the numbers would differ depending on the user's choice of compounds and temperature or pressure. Throughout the walkthrough of this code, you will notice that we wrote out commands that would plot graphs for each of the desired outputs. Now we head over to Matlab, and I will quickly run through each line of code to help you better understand how we got to our desired outputs. This project required a lot of data, and we found these components from the Antoine coefficient book in the Wayne State Library. We put the data in an Excel file, and then the types of data that this included was the number, formula, name, CAS number, A, B, and C constants, and the minimum and maximum temperature. So I'll open this Excel file just so you can see what I'm talking about. So right here, and then we imported it in. These numbers were, of course, different for each compound. All of the data from the Excel file got imported into Matlab, saved as a variable table file here, right here, and then sorted alphabetically. These are the prompts that we use to accomplish this, all through right here. Because the last column of data was not needed, we used indexing to remove it. The data then gets changed from a cell array to a table array. And string arrays are also created so the sequences can have different lengths without creating an error. Here's how we sorted the name of the material alphabetically and the compound number in descending order, right here. At this time, we had to fix some import errors like punctuation issues, and that concludes the portion of code involving data importing. Now moving on to the data selection portion of the code. Right here is the beginning of a very long while loop. And the purpose of it is to continue running and generating the code until the user decides it is time to end it. Right here, we changed the compound's formula from cell array to character array. And then this command here brings a pop-up list, or it creates a pop-up list so the user can choose an organic material. We then use indexing to retrieve the data about the user chosen material. We now do a similar pop-up list creation process, except this time the user gets to choose either pressure or temperature. Basically, the user inputs will help to index a table that contains the organic compounds and the Antoine coefficients. If the user chooses temperature, Antoine equation will determine pressure as a function of temperature. If the user decides pressure, Antoine equation will determine temperature as a function of pressure. An if-else statement will determine which function to execute based on user input. Right here is where this statement begins. We use seal and floor commands to round minimum and maximum temperature down to improve the usability. And then we needed to prompt the user to enter a temperature value. So that happens right here. We ended up using the compose command, and then the values are set for initial temperature and the compound constants. To have two vapor pressure points, Antoine equation will determine the vapor pressure at a standard pressure of 760 or 0 degrees Celsius. The standard temperature and pressure will be the initial condition. The temperature and pressure found from the user input will determine the final temperature and pressure. So right here, we come up to our first anonymous function, and it's created to evaluate initial and final pressure. And the compounds A, B, and C constants are used. Right here, we used another if-else statement to determine if the inputted temperature is valid or not. And then the fprintf lets the user know whether they need to try again or not. At this time, we reach our first graph. The purpose of it is to display the Antoine equation with initial and final temperature. And here's where we reach our first function file. The goal is to calculate the boiling point. And to do this, we used a nested for loop and the actual equation for boiling point. We call it in the script here, print the result for the user, and then we plot it. We also plot the user chosen temperature. The final and initial conditions are the information in the Clausius-Clapeyron equation used to determine the heat of vaporization. The heat of vaporization is the energy absorbed or lost as the substance vaporizes or condenses. In order to calculate the heat of vaporization, temperature must be converted from Celsius to kelvins, so that is done right here. This brings us to the next function file. This is another nested for loop that takes the user's inputted variables and Antoine equation. We followed this function up by plotting a pressure versus temperature graph, or you can call it the heat of vaporization. Then we created a fit of the line of heat vaporization using polyfit for graphing purposes. Next, the intercept of the Clausius-Clapeyron equation will be determined using the heat of vaporization to graph an exponential representation of the vapor pressure as a function of temperature. This is done in a separate function file right here, yet another nested for loop. Then the curve fitting tool will evaluate an equation for the exponential graph, and the exponential curve function file creates an exponential equation for vapor pressure. And that is seen right here. This function leads into our next graph, which is an exponential figure derived from Clausius-Clapeyron equation. We decided to add another sort of graph to this code, a histogram, and the purpose was to display and represent the distribution of the minimum and maximum temperatures, and polynomial regression will display to show the best fit for the temperature range for the chosen substance. That is the end of temperature. However, most of these steps would be repeated if pressure were to be the user's choice. The main difference is that the initial anonymous function will take pressure as an input. The minimum, maximum, and initial pressure must be declared. From there, the types of outputs and graphs are basically the same. You can see that this is where we would start with pressure. It's an else if, and so it's still in this big long if else. I'll just go through, show you that it's pretty similar throughout. And right here, we've reached the end of the big if else statement. So the code itself comes to an end with a switch case scenario that asks the user if they would like to run the program again. Now it's time to run the code so it's easier for you to visualize the bigger picture and how our goals came to life. So let's run this code. You'll see all of our organic materials pop up. You can scroll through and see how many there are. I'm going to select a random one. Then let's go with pressure. I'm going to go with 99 just for a random pressure. It has to be between 51 and this number. And you see it all pops up here. So it also it prompts us if we want to run the program again. For now, I'm just going to click cancel. You can see that all of these variables were created and put in the workspace. That happens all throughout the code in all of those loops, while loops, the for loops, switch cases, if else statements. You'll also see that a bunch of graphs popped up, but we'll get to those in a second. So looking at the command window, we can see that the pressure we put in is valid because it was in between the scenarios we made in the code. And then it displays the boiling temperature of the compound, and it says the boiling temperature, and then the heat of vaporization, the equation for the line of heat of vaporization, the vapor pressure of the compound, and the polynomial regression line. Now I'll go through each of these. They're in backwards order, but that's okay. So this is our polynomial regression line, and then the histogram, the distribution of maximum temperature, distribution of minimum temperature, the Clausius-Clapeyron equation, exponential vapor pressure graph, and then the heat of vaporization, and the Antoine equation. That concludes our project. Thank you so much for watching, and I really, really enjoyed this class and working on this with everyone. Thank you.